Yeah, sure. Hey guys, good morning. My name is Joshua Satten. I lead the blockchain practice for Wipro here in North America, and with me I have Hitarshi Buch, who runs our blockchain lab, and he's based out of India, one of our distinguished engineers. Basically today we have a real-life use case where it started off with our distinguished engineering group looking at just at how zero-knowledge cache worked and zero-knowledge proof worked, and then it turned into a larger conversation with the federal government in India, which turned into a specific conversation with the Telecom Regulatory Authority of India. And what we're talking about today is how you would use zero-knowledge proof on top of a distributed ledger network to have outsourced audits in a private and secure way for spam calls and spam texts. So they're trying to institute a system for 1 billion people in India that's going to allow people to blacklist certain callers, say I don't want to receive texts or emails or phone calls from this person on my device. I want to also have certain preferences for what kind of calls I do get. I'm interested in hearing from some types of people, but not other types of people. And we need to ensure that both the telemarketers and the communication companies are protecting those preferences and acting in a secure way at all time, and we need a way that we can actually penalize them if they're not. So, just to begin with, who we are, so it makes context, and then we'll roll into an actual demonstration on a video demo of how it works, and we'll show an actual example, 2 different ways, a pre-generated proof and then an on-demand proof, where it's stored or where it's generated when it's needed. So who we are, Wipro is a global organization that does blockchain implementation services. Zero-knowledge proof falls within our blockchain practice, and it's also a top focus area for our engineering group. The way that we're situated is we're typically working with large organizations who are looking to use distributed ledger and smart contracts on an enterprise level. So typically our partners are around cloud, blockchain as a service, or distributed ledger specifically. We're completely orthogonal. We work with Ethereum, Hyperledger, multi-chain, Quorum, you name it. We work across the board. We work with all the cloud providers. We don't have any set usage or any specific recommendation on who to work with. It's all client-specific use case. What we did on this network was the usage of Ethereum network with Ethereum smart contracts to build out, and then we put zero-knowledge proof within that. And looking at our partner ecosystem, we just wanted to highlight how interesting it is when we're working on these types of use cases. We're working with credit in terms of working with the Telecom Regulatory Authority of India, and they'll most likely be our partner in going forth in that proposal. But in just putting the foundation of the network together, we need cloud, we need distributed ledger, we need key management. We're working with the government regulator, and then of course we're here at Berkeley today and working with different associations in India and here in the US so that we can bring the research together with real-life application. In terms of how the services deal with it and how we work with them, it's full stack development, and where this comes into play in terms of how we work with DLT and zero-knowledge proofs is at the platform selection and DLT creation level, and then at the application management and standards level. And then again through testing when we go from POC to pilot into production, which is our clear goal. We don't want to build it out just for the government to play with it. We want to build a real solution that they're going to institute and hopefully have us work with them on for the long term. And then we always like to put up just how we break apart the different technical elements of blockchain and where we're coming to bear here today. Specifically, what we're talking about today is decentralized consensus mixed with a blockchain network and really secure identity and privacy. We want to ensure privacy across the board every step of the way. It's privacy for the government, for anybody they hire, for people who are citizens in India, and for any companies that are involved in the telecom industry. So, looking at the actual use case, it's examining the needs of the Telecom Regulatory Industry Authority in India. Here's how their market breaks out. There's content providers and telemarketers, and that's specifically who we're looking at for the most part. How do we make sure that telemarketers and content providers are only going and reaching out to consumers and people that allow them to or that want to hear from them? And how do we make sure that telecom service providers are storing preferences actively on an ongoing basis? So you should be able to say, I don't want to hear any more about shopping or sports, or I don't live in this geographic location, so I don't want to hear about this region. They should be storing that. There should be a way then for the Telecom Regulatory Authority to check that they are storing those preferences without being intrusive. There should be a way for them to also check that these content providers and telemarketers are ensuring that they're not going out to the wrong people on purpose, that they're checking these lists, and that they're ensuring that they're not spamming people. When you look at the size of the issue, and when you look at the size of the service that has to be built out, it's pretty huge. But the 2 biggest points that we're trying to break into here is A, the registration and deregistration processes, and then B, down here, how it's hard to verify and access these records. And we want to do it again in an unobtrusive way. And the ultimate goal of the regulatory authority is to build a system that they don't manage. They don't want to hire 1,000 people and then manage this long term. They want to outsource that and compartmentalize it with the group they trust, who's not going to then go into those records for any other reason also. So they need Chinese walls, so to speak, along the whole way. And looking at how it's grown, year by year by year, we're talking about blacklisting between 100,000 and 1 million different companies. We're talking about millions and millions of requests coming in for people to say preference changes or don't spam me or don't contact me anymore. So, Hitarshi, you want to?
Sure. Thanks, Joshua.
Pleasure.
Yeah. So we're going to focus on very specific aspects of the solution. The overall solution, is very holistic with the DLT in place. There is consent management. There is, a whole lot of other use cases around that. But from a ZKP point of view, we are going to focus on how the user preferences are maintained by the telecom service provider, which could be a Verizon or a AT&T, right? And ensuring that the messages or calls are getting filtered based on the user preferences, and providing a proof to the auditor without revealing the user preferences, because that is the private data which belongs to the subscriber, to the user, right? So the actual data cannot be revealed to the auditor or to anybody, because that would lead to a lot of spam messages, and invading the privacy of the user, right? So here the solution basically comprises of, 3 or 4 components. So one is the telecom service provider app, right, which allows the users to manage their preferences, right? So, and we'll shortly see how a typical user preference would look like. Then there is a scrubbing service, right? The scrubbing service basically filters out the messages sent by a telemarketer based on the user preferences, right? So the scrubbing service will rely on the privately maintained user preferences and filter out the events. The DLT network, in addition to the other use cases, it also is a ledger which captures the facts, the transactions as they happen, right? And it is an immutable copy which is available to all the participants, right? So whatever happened at a definite, time point, it is going to be captured in the DLT, and it serves as that proof. And finally, we are going to, use a ZK module, a zero knowledge module, which employs Socrates, which is a utility built on top of ZK Snarks, right? And it provides an ability to, generate a smart contract which will, allow us to verify the, okay, we are back, okay. Right, so which will allow us to verify whether the proof generated during the, I need to, sorry. All right, yeah, so which allows us to generate a, smart contract that, will verify the proof, right? So, and so we are going to talk about 2 approaches, right? One is to use the Socrates module, where the prover and the verifier basically are able to generate a proof and verify the proof, right? On demand, right? And that will be for each message request that is being sent and each phone number that has been processed by the scrubbing services. The second approach is based on Merkle trees, right? Because we see that Merkle tree is more efficient way of dealing with a large number of messages, large number of phone numbers, and the user preferences as they are managed, right? So the Merkle tree will get generated on the fly, and the Merkle proof is something which will be used by the verifier to see whether the actual user preferences were used while scrubbing out the messages before they are sent to the subscriber, right? So moving on. So the first approach is where, the telemarketer is going to send a delivery request, right? So this could be for any category of the message, and that's when the scrubber will basically get the user preferences from the telecom service provider, right, and start filtering the messages. As they filter the message, they will hit upon, for a particular phone number, a particular user preference, which matches that category, and they would store a one-way hash of it on DLT, right? So for that request ID and phone number, there will be a user preference hash which will be stored on DLT, which will represent that at that point of time, this was the user preference used, right? So, for example, today, if that message has been processed, and after 5 days, the auditor wants to know whether the message was filtered based on the user preference, we can use this source of truth on DLT.
So it's very similar to turning on Google ad personalization or not. So you can register or not register. If you don't register, you're going to get whatever ads come through. If you do register, you can either control them or you can turn them off to a full extent. But what the government's ultimately pushing for is making all telemarketers register themselves and then have to go through all of the cellular phone provider companies when they want to send any marketing messages out.
Sure. Right. So typically what would a user preference look like, right? So if you can see, there is a phone number, there are categories, and there are different attributes which would be used by the scrubbing service along with the version, right? So the users will keep on updating the user preferences. So the user preferences are going to be versioned, right? So this entire, so each record, if you see, is a unique combination, and the hash of it is something which is going to be stored on DLT, right? So I'm going to switch over to Putty and Postman for now, right? So let me try and maximize this. Right. Okay. Right. So here we are looking at the Scrubber API, right? So, oops.
Sorry.
I think, yeah, it's too sensitive.
There you go.
All right. Yeah, I need to. Right. So here for that request ID and the category, right, there is a message to be sent, and the Scrubber API basically filters the, or finds out which, which particular, preference has to be, used to filter out, and then there is a hash that is generated and stored on blockchain, right, on DLT. So this becomes the source of truth, which will become the public input, as we say, in case of, when we are using ZK snarks, right, for audit. So if we move ahead and if we want to, see what exactly is on the DLT, so we can use another API, right, so which should result in the same hash, right? So this becomes your public input. So I'm just going to record it here. And then the next API is something where we can retrieve the hash based on the request ID and phone number, right? And as you can see, it is the same hash that we had, right? So, so while we have the public input stored, right? So the next step is going to be, setting up of the Socrates framework, right? So that is a one-time activity which can be done for any prover and verifier combination, right? And once that setup is done, the prover is going to provide the private input. So in this case, the private input will be all the user preferences of a particular, related to a particular phone number, right? That will be the private input. And the private input is going to be compared with the public hash that was stored on DLT, right? So if I go back to my video here, right? So, as you can see, the public, so here I'm going to talk about now, at the heart of Socrates is the code file, right? So the code file basically takes into account a private input, right, which in this case will be the user preferences for a for a particular phone number, and we have taken the assumptions that there will be 10 user preferences at the max, right, belonging to different categories, right, and the public hash is something which is already stored on DLT because that's what the scrubbing service is stored, right, and as we loop through each of the private user preferences, we are going to hash it and compare it with the public input, right? So, and only when there is at least one match, that's when the the result of this circuit is going to be true, otherwise it's going to be false, right? So the next step is to, once we have this, code file ready, that's when we're going to, compile it, right? And there's a setup activity which will generate certain proving and verifying keys, right? So the next step is, basically compiling it, right? So as you can see, once it is compiled, it generates a human readable code file, right? And that code file is, going to be used to generate the proving and verifying key as well, right? And one thing to note is that things don't happen that fast in Socrates. It does take time, but since it is a video and we have a time limit, so certain things have been speeded up. So as you can see, we have the code. Sorry.
We timed it out.
Yes. Yeah. Right. So the next step is to do a setup, right? So there will be a proving key and a verifying key that will be generated, right? The proving key obviously will be used by the prover and to generate the proof. And the verifying key is something which is recorded as part of the smart contract, the Solidity smart contract, which will get recorded onto. Okay, I think. So here, what I'm doing. Sorry. Right. So after the setup part, right. So here we have the verification key and the proving key, right? And the last step is, as I said, generating the Solidity smart contract, right, which will sit on the DLT and used for verification, right? So as you can see, the Solidity file has been generated, right? Now the next step, obviously, is to is to basically create the private input, right? So the private input, as we know, for a particular phone number, for the latest version would contain 10 records, right? And as Socrates, accepts numerical input only, so we are going to convert that into a numerical input and then, use it as the private input, right? So here, as you can see, the user preferences got converted into numerical input, and that is something which is going to be fed into the circuit, right? So this is the private input. So sorry for the typo, So and so here the public input becomes the hash that was on DLT. The private input becomes the user preferences that were retrieved from the TSP database, right? And this is something which we are going to use and generate the proof, right? So a proof JSON is something which gets generated, right? And as you can see in the behind the scenes, the Socrates command has run to generate the witness and the proof, right? And this proof is something which we can use to basically, it can be used by the auditor to find out whether the inputs provided, the public hash, right? So whether it is valid one or not, right? So once we run the verify function, so what it will do is it is going to compare this input with what is there in the Solidity smart contract, right? It will verify the verifying key, right? And ultimately it will return a success or a failure message, right? So if we are going to change the input at any bit of the input here, for example, I change 99 to 00, it will, result in a false, output, and so the auditor knows that something went wrong, and we need to do some further investigations, right? So this is about the technique to use, on demand. So here, as you can see, for each request and a phone number, we are able to generate a proof which the auditor can use to find out whether the processing of the messages was based on the user preference or not, right? While this is a good technique, of course, there are some limitations because as to how ZK Snarks operates, right?
It's slow and it's not very scalable.
Right.
So we need something faster. Enter Merkle trees.
Right. So here, okay. Yeah. So the second approach is, to use, to construct a Merkle tree for a particular request, right? So whenever a scrubber receives a message request, right, say send out a message about movies, right? So they might be processing 10,000 phone numbers, right? So the user preferences of all those phone numbers will be used as the leaf nodes to construct a Merkle tree, right? And that Merkle tree is something which can be used by the auditor to verify whether a particular phone number's preference were used for scrubbing or not, right? So
And since we're using a DLT, and since the preferences are captured immutably, that's representing all these records that are being appended over time. So as your preferences change, as more people join or get off the network, it's exponentially more records that need to be checked and need to be built out.
Right. So here the role of the DLT, is basically to capture the root of the Merkle tree, in a timestamp manner. So at a given point of time, when the Merkle tree root is generated, that becomes the source of truth. And at a later point of time, when an auditor seeks for proof, right? So that's when the Merkle proof can be used to recalculate the Merkle tree, right? So if we see, I can't move here. So as we can see here, there are phone numbers, right? And the preferences related to those phone numbers become the leaf nodes, right? So the hashes H1, H2, H3 are a representation of the hash of the user preferences, right? All the user preferences of a phone number, and they all culminate or combine to become the Merkle root, right? So with that, we also provide two random phone numbers, M and N, which can be used to by the auditor to generate the Merkle proof, right, and recalculate the Merkle root, right? So for example, in case of M, which is in green, right, all I need to know is H2, H1, and H3, H4, 4, right? So to arrive at the Merkle root. So not all information needs to be revealed, even for the hashes, right? It is a very fast and efficient way. It is Merkle tree is something which is used in leading blockchains like Bitcoin and Ethereum. So similarly for N, all you need to know is about the blue boxes that have been highlighted, and that's how ultimately when the auditor wants a proof, right? So the hash of the leaf node is something which the TSP telecom service provider can provide, and based on that leaf hash, the Merkle path can be found out from the tree, and that is something which is used as a Merkle proof to recalculate the Merkle root which is present on the DLT. So finally, the smart contract is going to compare this recalculated root along with what was stored originally on DLT, and that's how it's going to decide whether the user preferences used at that point of time match with what the TSP is currently maintaining as of today, right? So that's how this is the second approach, and we felt that this is more scalable because Merkle trees can accommodate a large amount of hashes, and traversing through the Merkle tree is also very efficient, right? So yeah. So from prototyping point of view, I think Socrates is providing a much better means of having on-demand proof, and allowing the prover and verifier to exchange the information, right, without revealing the user preferences, right? So that's what I wanted to cover, and we still have 1 minute 40 seconds left.
Any questions? Thank you. Any questions? Anyone?
Either one of you guys. You want to join?
Sure.
Yeah, go ahead. Right here in the second row. Yeah. And then we'll get you second back there.
Yeah, I have a question about the user preferences. You said there'll be 10 altogether, or is?
No, there was 10 classifications that they were storing.
Right.
10 fields.
Yeah.
That would store different types of preferences.
Right. So here, if you see, for one phone number, there are 10 categories, right? Sports, entertainment. So there are 10 unique categories, right? And for each category, the user will have a preference, whether they are interested, which time window they want the message to be delivered on, right? And the frequency, and there could be many more, right? And each of these records is going to be versioned, right? Because the user will keep updating the user preferences.
So this is how it would look in a DLT. If you're keeping version records, if you were thinking about this for yourself in real life, it'd be flipped on its side. It'd be your phone number and then 10 categories: banking, finance, sports. I want to only hear about football. I want to only hear about retirement services. That's what we're getting down to. 10 highlighted categories where you would set preferences for each category of what kind of information you want to get and when.
Okay. Would it be possible? So do you hash each row? Is that
Yes. So each row is hashed. So because each row becomes a unique combination, right? So we.
Each record becomes a hash in the Ethereum network that we built out.
My last question, would it be possible for someone to guess like what the inputs are?
Right. So the phone number can be found out, right? And but what we store on DLT is a combination of request ID and phone number, right? And a salted hash of it, so that becomes the key, right? Because in blockchain typically it's a key value pair, so that becomes the key, and the value becomes the hash of the entire thing, right? And it's a one-way 256-bit hash. So brute force hacking would be difficult, if not impossible.
Thank you very much. Let's thank the speakers.
All right.
I thought there was more questions.
We just ran out. Sorry.
Okay.
Thank you guys.
All right. Thank you.